Hello everyone, my name is Tarun Malhotra. I am a lead software engineer here at InterviewBit and also take classes at Scalar Academy. Today's session is going to be a session which deals with basics of dynamic programming. That is, what is this paradigm? What kinds of questions can you solve using this paradigm? And we would try to solve some simple problems on DB today. But going forward, as and when we move on with these sessions, you should be able to be more and more confident with the idea of DP and how to apply dynamic programming in the problems where you can actually model those problems as DP problems. Okay, cool. So before actually coming to the definition of dynamic programming, describing what this paradigm is, let's take an example by which, with whose help, we'll actually figure out that what is the reason of coming up with a paradigm like this. Okay, what kinds of problem can you actually hope to optimize further using this paradigm of dynamic programming? Cool. Yeah, the very first problem that you'd want to see without actually knowing about DP would be the problem of Fibonacci numbers. I am sure that most of you would have heard about this problem of Fibonacci numbers. The problem is as follows. You want to figure out the nth Fibonacci number, and the Fibonacci numbers are as follows. The first Fibonacci number, by definition, would be equal to, let's say, 1. The second Fibonacci number would be equal to, let's say, 1 again. And now, for any Fibonacci number n, where n is greater than 2, the number can be defined using the previously defined Fibonacci numbers. Okay, so for fn, where n is greater than 2, you can say that the nth Fibonacci number would be equal to the summation of n minus 1th Fibonacci number plus the n minus 2th Fibonacci number. I hope this definition should be clear to everybody. The first Fibonacci number is 1, the second Fibonacci number is 1. Now, and for any n which is greater than 2, the nth Fibonacci number would be the summation of the last two Fibonacci numbers. Okay, the n minus 1th and the n minus 2. Now, I am pretty sure that just by looking at the definition of Fibonacci numbers, everyone would be clear that the definition of Fibonacci numbers is nothing but a recursive definition, right? You are actually defining a number recursively using the previously defined numbers. Okay, so how would you go about solving this? The problems of recursion can actually be very easily visualized by drawing a recursive tree. I hope all of you should be able to appreciate that. Let's take an example and see if we are able to appreciate that completely. Okay, so let's say I wanted to compute the 7th Fibonacci number. Okay, I wanted to compute the 7th Fibonacci number. So let's say, yes, this is a state that I want to compute the 7th Fibonacci number. Now, by definition, if I want to compute the 7th Fibonacci number, I should go to the number n minus 1th and the number n minus 2th. Okay, so f7 would actually be nothing but a summation of f6 and f5. I hope this should be crystal clear to everybody that this is just a recursive definition. Now, we do not know what f6 is, and f6 can again be computed using the same definition that we have given above by saying that f6 would be nothing but f5 plus f4. You can keep on drawing this tree, and now f5 can be represented by, let's say, f4, f3. f4 can be represented as the summation of f3 and f2, where f3 can be represented as the summation of f2 and f1. Now we know that we need not define this f2 into smaller subproblems, because by definition, I already know that f2 is equal to 1 and I already know that f1 is equal to 1. So now I know that the answer to this is already known, so no need to divide it further. The answer to this is already known, no need to divide this further. The answer to this is already known, no need to divide it further. So we call these cases, which are trivially easy to answer themselves in any recursive problem, as the base case of a recursive problem. Okay, so also just to give a context why we are discussing about recursion should be very clear in a bit when we actually move from recursion to DP. So just hold on for a while and understand this properly. Okay, so this would be a base case. This would be a base case. That is a problem for whom we know the solution already. This would also be a base case. Now, is F3 a base case? No, F3 is not a base case because I do not know the answer of F3 already. So I would define F3 into smaller problems as the summation of F2 and F1. Now, F2 is a base case and F1 is a base case. Now, let's come to the node which is still remaining, F4. You would realize that this F4 would again be expanded as an entire subtree. Does it make sense? F4 would be expanded to the summation of F3 and F2, so on and so forth. F3 would be expanded to a subtree. F2 would be again expanded to a subtree, and this would go on. And you can also look at F5. This would also be expanded to a subtree where the base cases would only be F2s and F1s. I hope this makes crystal sense to everybody. So we represented this Fibonacci problem as a recursive tree because it's a recursive problem. Now, once I have defined this, now to compute this problem, you will essentially have to compute every single node in this recursive tree, right? You can start from the very top and then you will be computing every single node in this recursive tree. Now the problem arises that how much time would I actually require to compute the value of F7 or any F9? To compute the value of F7, I will have to compute this entire tree. So to estimate the time required to compute that, I would suggest that let's first of all estimate the number of states that are there. Okay. From looking at this diagram and realizing it intuitively, you would realize that first of all, what is the depth of this tree, right? So you start with F7 and what is the farthest distance where you would be actually finding a base case? The farthest distance would actually be 7 in this case because you started with F7. And in each iteration, at each level, you at least have one node which was just reduced by 1. Okay, so the depth of this tree is 7 in this case, or to speak generally, the depth of this tree would be n if you are computing the nth Fibonacci number. Okay, if the depth of the tree is n, the fan factor of the tree is 2, you would realize intuitively that the number of states here would be of the order 2 power n. I hope this makes sense to everybody. The number of states would be of the order 2 power n. Now, let's actually figure out the amount of time required to compute a state. That I would claim time required per state in this case is nothing but a constant amount of time. Let's call it order 1. Why? Because if I want to compute this state and I already know the answers to F4 and F5, I just need to add them up. So the time required per state, if you are already assuming that you know the states below it, would be order 1. There are 2 ki power n states to be computed. Every state would be computed in order 1 time. So time complexity is definitely going to be exponential, is definitely going to be 2 power n. This is one way to look at it. The other way to look at it would be solving the recurrence relationship. The recurrence for this problem would be that you have a problem of size n. You are reducing that problem of size n to a problem of size n minus 1 and a problem of size n minus 2. And you are combining them by spending some constant amount of time. If you solve this recurrence, you will again get the same time complexity, which is exponential time complexity 2 power n. I hope till this point in time, everything makes sense that to solve a Fibonacci number, you are essentially giving exponential time. Now let's actually draw some observations in the tree that we have just formulated. The observation that I want you guys to draw, that there are a lot of states that you are computing that you could have avoided computing. Okay, listen it again. I am saying that there are a lot of states here which could have been avoided. You could have avoided computing them just because you already knew the answer of those states. Okay, let's see some examples. So have a look at it. You have already computed f of 3 here. Does it make sense? But you are again seeing this f of 3 here. And that's not a... When you actually solve this f of 4, you again solve f of 3 here, right? And when you actually solve f of 5, you are essentially going to solve f of 4 and f of 3. This f of 3 is again repeated. To solve this f of 4, you are again going to call f of 3, which is again repeated. So you see that there is a lot of repetition happening here in the states that we have defined. Okay, in this recursive tree, there are a lot of repetitions. and you could have actually avoided doing those repetitive computations. Try to understand it's not only about one state being repeated, it's about so many entire subtrees being repeated. Okay, so if this F3 was already known, you could have avoided computing this entire subtree. Now, if this F4 was already known, you could have avoided computing this entire subtree. If this F5 was already known, you could have avoided computing this entire subtree. And this, if F2 was already known, which is a base case, you could have avoided computing this subtree. And this F1 is again a base case. You can just remove it because that's a problem that you already know, or you can assume that F2 could have been divided into F1 and something. And this is, so basically this is just a base case. So now you actually see that the problem, which was a binary tree in the beginning, is now reduced to nothing but a linked list. Does it make sense? There is no tree here now. The recursive tree is no longer a tree in this case, just happens to be a list of some states that you are computing. Okay, so you see that the number of unique states that you have, is just of order n. You only have order n unique states here, but in the recursive tree you had 2 power n states, and now you actually get the idea that you could have actually stored the values of these states, and whenever you wanted to get those values again, rather than recomputing them, you could have just utilized the answers that you already had. I hope this makes sense to everybody. So we have actually reduced a problem which had so many number of states into a problem with lesser number of states, just because the number of unique states that I had was smaller than the number of total states that I was seeing. Okay, so this is the basic idea. Now let's actually come to the definition of dynamic programming and see how this idea can be extended and can be utilized to solve a lot of problems. Okay, cool. So let me actually take you to one interesting definition of dynamic programming. A way to put it would be that dynamic programming is a method of solving complex problems by breaking the problem down into collection of simpler subproblems. So you have a bigger problem. You are breaking that bigger problem into a collection of smaller problems of the same type. Now you end up solving those smaller problems exactly once, and then you utilize those solutions to construct the answer to a bigger problem. Okay, so what exactly you are doing? Let's look at this problem. That you have a problem which could have been solved using smaller subproblems. So Fn could have been solved using the answers to smaller subproblems, where n would be less than this n dashed. And now you end up solving those subproblems exactly once. So you are only going to solve F6 exactly once, F5 exactly once, F4 exactly once, and so on and so forth. And you are then going to utilize the answers to those smaller problems to construct the answer to a bigger problem. Okay, so this is exactly what we will end up doing here. Let me actually just tell you how we can solve this problem here, right? So you know this is a recursive problem. So a simple recursive code of this solution would be that, let's say you wanted to solve, let's say you want to return an int, you want to say int get Fibonacci number. It takes as input the nth Fibonacci number that you want to return. So this is a recursive code. In any recursive code, you start with the base case. This is something that you should always remember. So you start with the base case. The base case here happens to be n equal to 1 or n equal to 2, right? So what do? You say, first of all, let's check for a safety case that if n is less than less than 1, then let's say it's not defined. So you return -1, let's assume. Now, if this is not the case, if n happens to be less than or equal to 2, that is, if n happens to be exactly 1 or 2, that is, you want the first Fibonacci number or the second Fibonacci number, you are just going to return 1. This is the base case that we have by definition. Now, after this, for any other n, you would simply be calling f of n minus 1 and f of n minus 2. So a simple recursive solution would look something like this. That's simply going to return get fib for n minus 1 plus get fib for n minus 2. This is a simple recursive problem. but you see a lot of recomputations are happening here. So what do? You just add memoization. So what do? This is plain recursion. In plain recursion, you just add something which is called as, let's say, memoization. Just because you see a lot of states being recomputed again and again. So rather than recomputing them, let's actually store them and only compute them exactly once. So how to store them? Let's say you now have an array of size, let's say n, which is initialized by, let's say, -1 to begin with. Make it n plus 1 if you are using it. Let's assume this was one indexing array. Okay. Now you initialize the base cases here by, or let's say, you can initialize the base case here by saying that f of 1 would be equal to f of 2 would be equal to 1. And now what do? When you actually want to compute that, you first check if that n minus 1th value was already computed or not. So rather than just doing this, you actually do something else. So now you first check if f of n minus 1 was still equal to -1, that is, it was still not computed, only then you make a call to compute it. So you now say f of n minus 1 would be equal to get fib n minus 1. You now have the value here. Similarly, you do that for f of n minus 2 and see if that is equal to -1. You compute the value and store it there. And then once you have done both of these operations, you simply return the summation of them. So just by changing the solution a bit, you have reduced a lot of time complexity. The time complexity now becomes order n. Okay. The space complexity also becomes order n. Cool. So this was a very, very basic problem. Let's move ahead. You can actually reduce the space complexity, but let's leave it as a homework for you guys to understand that how you can actually reduce the space complexity here. So now let's actually move to a lot more interesting problems on dynamic programming. And before that, let me give you the formal definition here, which will help us to figure out when to use dynamic programming. Okay. So the formal definition of dynamic programming is that a problem which can be modeled, into dynamic programming if it has two features. So what are the features for a problem to be modeled in dynamic programming? The first feature is that the problem exhibits optimal substructure. What is optimal substructure? We'll just come to it in a moment. The second feature is that you should be seeing overlapping subproblems. So these are the two features that you look in any problem to make sure whether that problem can be solved using the dynamic programming paradigm or not. Now let's explain these two features in more detail. Okay. Optimal substructure feature simply means that your problem, the solution to the problem, the optimal solution to a bigger problem can actually be constructed using optimal solutions to smaller problems. Okay. So the optimal solution to a bigger problem can be computed using the optimal solutions to smaller problems. So this is the optimal substructure property. That is, let's say here you want to compute f of 7. Can you actually compute f of 7 using the smaller problems answers? Can you compute it using f of 6 and f of 5? Yes, you can do that. Right? Can you compute f of 6 using f of 4 and f of 5? Yes, you can do that. So a problem which shows that you can compute an answer to a bigger problem using the solutions to smaller problems is called as optimal substructure. The problem being showing optimal substructure. Okay. The second part is that you should see a lot of overlapping subproblems. Okay. So what is overlapping subproblems? That is, you should be able to see subproblems which were otherwise being repeated several times, and now you can just memoize them so that you do not compute the same problem again and again. Okay. So just because a problem which exhibits overlapping subproblems, you see an opening that yes, you can exploit that overlapping subproblems and reduce substantially the number of subproblems that you actually compute. Okay. So overlapping subproblems. That is, you should see a subproblem being computed again and again. The moment you see that, you can stop doing that, and then you call your solution to be a dynamic programming solution. Okay. So you see subproblems being computed multiple number of times. Now, these are the two features which will help you to judge whether a problem can be solved using a dynamic programming paradigm or not. Now, keeping this in mind, let's try to solve a few problems, and then we would keep on building on the concepts using those problems. Okay. The very first problem that I would want to discuss with you guys is called as the problem of stairs. So this is a problem that is actually asked in several product companies. This problem was asked at Morgan Stanley. This problem was solved at Amazon, was asked at interviews of Amazon. This problem was also asked at interviews of Intel. So this is a problem which you, just by looking at the companies that have asked this problem, you guys would have gotten an idea that yes, this happens to be a very, very interesting application of dynamic programming. Okay, cool. Let's define the problem. The problem is as follows, that you have n stairs. Okay, you have n stairs. So let's call it the first stair, the second stair, the third stair, and let's call it the nth stair. You have n stairs. Let's assume originally you are at the first stair. Okay, so originally you are at the first stair. Okay, now at every stair you have two options. Option one that you have is to just from the ith stair go to the I plus 1th stair. The second option that you have is that from the ith stair you go to the I plus the second stair. So I plus 2th stair. Okay, so what does that mean? So let's say you were at the first stair. The first option that you have is to go to the second stair, or you could have actually chosen to directly jump to the third stair. You could have avoided going to the second stair and directly jump to the third stair. These are the two options that you have. The question asks you that you want to figure out the number of ways to reach the nth stair from the first stair. What does that mean? That how many distinct number of ways are there in this problem which will take you from the first stair to the nth stair. I hope the problem is clear to everybody. Okay, cool. Now let's actually look at a couple of examples and see what kind of a pattern do we observe. Okay, let's take an example for what happens if the number of stairs was only equal to 1. So let's say there is only one stair. You are at the first stair, you only have to reach the first stair. How many number of ways that are there? The number of ways that you have is only one. That you can choose not to do anything because you are at the first stair itself. You cannot do anything else but to stay at that stair. Now let's look at the example 2. What happens if you have n equal to 2? That you happen to be at the first stair and you have to reach at the second stair. How many distinct ways do you have? So you have at the first stair, you have two options, either to go to the second stair or the third stair. The third stair does not exist. So there is only one option, that you can just go to the second stair. And the moment you go to the second stair, you have reached the solution that you have. You can only stay there, cannot go anywhere else. So the number of ways for this n equal to 2 problem would also be equal to 1. Now let's look at the example 3 that we have. So let's say now we have n equal to 3. You are at the first stair, you want to reach at the third stair. What all options do you have, people? You are at the first stair, you have two options. Either from the first stair, you can go to the second stair, or you have the second option which says from the first stair, you can go directly to the third stair. Okay? If you actually choose to do the second option, that is from the first to the third, you have already reached your destination and you can only stay there. You cannot do anything else. Now let's look at the first case that you assume that you can move from the first to the second. If you move from the first to the second, what options do you have from the second stair onwards? You can either go to the third stair or you can jump to the fourth stair, but fourth stair does not exist. So you only have one option, that is to go to the third stair. Now this also completes the entire path and you have reached the solution. So you see that there are two ways to solve this problem. If n was equal to 3, the number of ways that you have is 2. Does it make sense to everybody? We have seen 3 examples here. N equal to 1, n equal to 2, and n equal to 3. And we now know that what are the number of ways that you have to reach to your nth stair. Cool. We have understood the problem. Now let's see, can we, so how I would approach to a greedy problem. Okay. One thing that I just told you, that it's very important to check whether these features are there in the DP problem. So let's check whether these features are actually there in the DP problem. The first feature is there an optimal substructure? Okay. So do you see an optimal substructure? What does that mean? Can you solve a bigger problem using the answers to smaller problems? Okay. So let's try to answer that. Let's take any bigger problem. Let's take n equal to 5. Let's assume that you had 5 stairs. Now let's assume if you want to compute the number of ways to reach the 5th stair from the first stair, and somehow you already know the answer to number of ways to reach the 4th stair and the number of ways to reach the 3rd stair. Let's say somebody told you that number of ways to reach the 3rd stair is equal to A, and the number of ways to reach the 4th stair is equal to B. Now, can I actually compute the number of ways to reach the 5th stair? Okay, let's try to find out. So if I want to reach the 5th stair, you guys tell me what are the options that I have for the penultimate step. If the last step that I make happens to be the 5th stair, that is I want to reach the 5th stair, what options do I have for the penultimate stair? That is the second last stair that I would have taken. The option 1 that I have for the penultimate stair is that I would have been at the 4th stair. Does that make sense, guys? From the 4th stair, you could have gone to the 5th stair. This is one option. The second option that you have for the penultimate stair would be that you could have actually gone from the 3rd stair to the 5th stair. I hope it makes sense. The options that you have for the penultimate stair would either be from the 4th stair or from the 3rd stair. Okay? So you could have actually, one option is you could have come from the 4th stair to the 5th stair. The other option is that you would have come from the 3rd stair and jumped directly to the 5th stair. Now, I know the number of ways I would have reached the 4th stair from the 1st, which is nothing but B. If I know that from the 4th stair, I only have one option to go to the 5th stair, which is just to take a single step, I will multiply this by 1 because I only have one option from the 4th stair. So B into 1. Then the second option was that I come to the 3rd stair somehow and then jump directly to the 5th stair. If I come to the 3rd stair somehow, number of ways I already knew, let's assume was equal to A. So I do A. And now from 3rd to 5th, if I want to have a jump, I will just multiply it by 1. These were the two mutually exclusive and exhaustive options that I had. So I will just add them up to get my complete answer. So number of ways to reach the 5th stair from the 1st stair would be nothing but the number of ways to reach the 4th stair multiplied by 1 plus the number of ways to reach the 3rd stair multiplied by 1. Okay, you can actually generalize this and say that number of ways to reach the nth stair is nothing but number of ways to reach the n minus 1th stair multiplied by 1 plus number of ways to reach the n minus 2th stair multiplied by 1. So this also happens to be a problem which very interestingly mimics the problem that we had for Fibonacci numbers. Does that make sense to everybody? Have we actually just proven to ourselves that we see our optimal substructure here, that we can actually solve a bigger problem using smaller problems? If you can see that optimal substructure is there, using that we have arrived at a recurrence relationship as well. Now looking at this recurrence relationship, we also see that a lot of states would be repeated. So yes, there is an overlapping subproblem point here as well. So this problem can be very easily solved using dynamic programming. Does that make sense to everybody? That you have actually proven to yourself that this problem actually has overlapping subproblems and optimal substructure both. So you can solve this problem using the dynamic programming way. Cool. So once we have established that how to look at a problem and figure out whether you can solve it using DP approach or not, let me actually describe to you two ways to solve a DP problem. Okay. So this is one way to look at a DP problem. Hold on for a while. In the next question or so, I would be discussing another way of looking at DP problems and solving them. In the meanwhile, let me tell you that there are two broad ways to solve any DP problem. Okay. One of them happens to be a top-down approach. What is meant by a top-down approach? A top-down approach means that you just write a recursive code as we did in our first problem for Fibonacci, and with the recursive code, just because you see that there are overlapping subproblems, and you can actually reduce the time complexity by memoizing those subproblems, that is storing the answers to those subproblems. You can just in the recursive code just throw in memoization, and you would get a solution for the top-down approach using DP. I hope it makes sense. That what did we do in our first solution? We just wrote a recursive code and just added memoization. That is, we just added an array where we actually just added some states where we actually stored the answer to those states and did not compute them again. So a simple recursive problem code with throwing in memoization in it would actually solve your problem top down. Why do we call it top down? That you actually start solving your problem from the answer that you want. That top problem gets divided into smaller problems, and this keeps on happening. So you move from the top to the down. This is one way of solving DP problems. The second approach of solving DP problems is bottom up. What does that mean? The bottom up approach means that you actually start constructing your DP solution from the base case. Okay, so you actually have the answers to base cases already. This is what we know. You already have the answers to base case. Using the answer to those base case, compute the state that you could have computed just by using those answers. So in case of Fibonacci, if I know the answers to f of 1, which is a base case, and f of 2, which is a base case, both of them were equal to 1. Using these two, can you tell me what state can I compute? Using these two, I am pretty sure that you guys would be able to appreciate that you can compute, using these two states, you can compute the third Fibonacci state, which is just a summation of f1 and f2, which happens to be 2. Now you are constructing your solution bottom up. You start with the base cases and you keep on constructing your solution. Now you have the answer to f of 1, f of 2, and f of 3. Which state can you compute using this information? So my suggestion would be that you can now use the answer to f of 2 and f of 3, and you can compute the answer of f of 4. Does that make sense? It would just be the sum of them, which would be equal to 3. Now you have constructed the answers till f of 4. Now you can construct thereafter as well. So now you can use the answer to f of 3 and f of 4 and create the answer to f of 5, which happens to be just the sum of them, which happens to be 5. So you would see that you can just keep on creating answers, constructing answers in the bottom-up approach as well. So this was the first answer that you knew just by the base case. Second answer that you knew just by the base case. The third answer that you computed was this. The fourth that you computed was this. The fifth that you computed was this. And the sixth would be just using f of 4 and f of 5, you can compute f of 6, which would just be 3 plus 5, which is 8. And this would be the sixth step that you compute. So you now understand that there are two ways to solve DP problems. You can either write your code in a top-down approach, which is recursive plus memoization, or you can write your code in a bottom-up fashion, which is just by using the base cases, you keep on building your solutions to bigger and bigger problems. Okay, so this was just a big bit of a digression that we took to explain that to you, that different ways of solving DP problems. Before that, we made sure that all of us understand that DP problems that can show the features of optimal substructure, that is a bigger problem being divided into smaller problems, and utilizing the answers to smaller problems to solve the bigger problem. This is the first feature that problems being solved using dynamic programming paradigm should have. The second feature that we have is of overlapping subproblems. That is, when you divide a bigger problem into smaller problems, you see a lot of smaller problems being overlapping, and you can optimize them by having memoization, that is storing the value somewhere, and the next time you see the same problem, just utilizing the value and not computing it again. So these are the two features that any problem should show if you have to solve that problem using dynamic programming. Cool. Now let's move ahead, and then using the next question, I would try to explain to you guys that what is the difference between greedy solutions versus dynamic programming solutions. So we would look at a problem and see in what problems do you see greedy solutions not being able to solve the problem for you, and you choosing to go to a DP solution. Okay, cool. The problem is a problem, which is again a very famous problem, problem of robbers. This is the problem of robbers. This problem again, we have seen this being asked in the interviews of Amazon, and we have asked this problem being asked in the interviews of the shop. Okay, so these are the two companies that we have seen this problem being asked at. Now the problem is as follows: you are a robber. Unfortunately, you are a robber. Okay, you see a street where there are n houses. You see a street where there are n houses. Every house has some gold coins in it. Okay, so let's assume the first house has 2 gold coins, second house has 7 gold coins, third house has 9 gold coin, 3 and 1. So these are the gold coins that are present in these houses that you see on a single street. Okay, now you are a robber. So what would you do? You would want to rob these houses. Okay, what is the function that you would want to maximize? You would want to maximize your robbery. Does that make sense? So if unfortunately you happen to be a robber, what would be your optimization function? That you would want to maximize your robbery. Okay, if you want to maximize your robbery and there was no constraint, then you would have actually robbed every single house. Does that make sense? Right? But let's now add, to make the problem interesting, let's add a constraint. The constraint is as follows: that every 2 adjacent house on the street are connected by an alarm. Okay, so you see an alarm between the first and the second house. You see an alarm between the second and the third house, between the third and the fourth house, the fourth and the fifth house. So you see there are some alarms being placed between every 2 adjacent house. What does that alarm do? That alarm simply rings if any one of these 2 houses are being robbed. So what does that mean? It means that if this house is being robbed by you, this alarm would go up and this alarm would also go up. So if this alarm goes up, the people in this house will wake up and you will no longer be able to rob this house. Similarly, if this alarm goes up, people in this house will also wake up, and unfortunately or fortunately for them and unfortunately for you, you cannot rob this house also. Okay, so this is the problem, that the moment you rob one house, there are your left house and the right house now cannot be robbed. I hope everybody gets the problem. Okay, how would we go about solving it? The answer to that, so let me just remove the things that I just drew over this problem, and let's first of all see, can I actually come up with a greedy solution to this problem? So before actually answering, can I have a greedy solution, let me actually define for you very quickly what a greedy solution is. A greedy solution is that without looking at what holds for you in the future, without looking at the future numbers, can you just make a call by looking at the number that you are just seeing? By looking at the thing that you are just seeing, can you actually figure out the solution to the entire, can you actually make a choice by looking at the current number? So what does that mean? You can claim that you have a greedy solution if you can think in this way, that just by looking at this house, the first house, can you make a decision of robbing this house or not robbing this house? Just by looking at the first house, can you make a decision of robbing this house or not robbing this house? Is it possible? You cannot. Similarly, can you say, I will never rob the first house? You cannot do that. You will actually have to look at the houses thereafter to figure out whether robbing this house makes sense or not. Right? Why do I say so? Because the moment I rob this house, I am changing the landscape of the problem. The moment I rob this house, I am enforcing a constraint on me that I can no longer rob this house. Does that make sense? And without looking at what holds for me in the future, would I ever be fine with imposing these constraints? No. So that is why I would tell you that greedy solution here would not work. Just by looking at this 2, you cannot make a decision whether to rob it or not. Similarly, just by looking at this 7, you cannot make a decision whether to rob it or not. So the problems where you have a choice, the problems where you have a choice and you cannot take any choice greedily without looking at what holds for you in the future, greedy solutions won't work. So here, greedy solutions won't work. That may make us a bit unhappy, that why greedy solutions are not working here. Okay, so let me just define the problem again. Whenever you see a choice or a set of choices, you see a set of choices and you cannot make a greedy decision, greedy problems won't work. Okay, so now if greedy solutions won't work, let's actually try if we can see that a dynamic programming solution can work. What does a dynamic programming solution do? It essentially allows you to explore all the possible choices that you had. So what does a DP solution do? The moment you see a set of choices and you see that you cannot make a choice randomly, you cannot just greedily make a choice, DP solution would say that let's explore all the choices that you have. DP solutions would allow you to do that. That you can actually explore all the choices that you have. And if you can explore all the choices that you have, then you can think in DP direction. Greedy won't work. Let's think the dynamic programming way. Before actually making sure that, before actually jumping to dynamic programming, let's see if the two features that we discussed before, does those features hold for this problem or not. The first feature that I told you was, does this problem show optimal substructure? What does that mean? If you know the solution to a smaller problem, can you know the solution to a bigger problem? Okay, so let me prove to you guys that yes, this problem does have optimal substructure. Okay, so let's actually come to the first feature that we had of optimal substructure. Let's actually prove to ourselves that yes, optimal substructure as a property is being held in this example. Okay, how to prove that? Let me give you an example. So let's say somebody told you that, hey man, don't worry, I know the best answer for robbing houses till this point, till the first 4 houses, and I'm telling you that I definitely robbed the last house. Okay, so I'm telling you the best answer, the best number of gold coins that I can accumulate by robbing the first 4 houses and making sure that I rob the 4th house would be something like this. Okay, somebody told you this answer. Let's call it maximum robbery for the first 4 houses. Somebody also told you the answer to another question, that I am robbing the first 3 houses, man, and I have definitely robbed the 3rd house. I also know the answer to that. So somebody tells you that yes, maximum robbery 3 ka answer you already know. Now if you know the answer of maximum robbery 3 and maximum robbery 4, can you actually construct the answer of maximum robbery 5? Yes, you can do that. Why you can do that? Because for the 5th house, you have 2 choices. Either you can rob this house or not rob this house, right? If you choose to rob this house, what is the constraint that you are imposing on yourself? The constraint that you are imposing on yourself is that you can no longer rob the 4th house. Does that make sense, people? If you're robbing the 5th house, the constraint that you're making on yourself is that you cannot rob the 4th house. So what is the house that you can rob now? You can rob the 3rd house for sure. So if you want to answer of maximum robbery 5, you can either choose to rob that house. If you choose to rob that house, how many gold coins are you accumulating? You are accumulating the gold coins at the 5th house because you're robbing it, right? So you're accumulating the gold coins at the 5th house. Now your problem reduces to finding the best gold that you can accumulate by robbing the first 3 houses. So you get maximum rob 3. This is one option that you have. That was you wanted to rob the 5th house. If you do not rob the 5th house, what is the option that you have? If I do not rob the 5th house, the gold coins that I'm robbing from the 5th house would be 0 because I'm not robbing it. And if I'm not robbing it, am I imposing any constraint of not robbing the 4th house? I am not. So I will just use 0 plus max rob 4. I have these 2 options. The best answer out of these 2 options I will take. So I will just say that the maximum out of these 2 would give me the answer. So either I can rob the 5th house or I can not rob the 5th house, and the maximum of these 2 would give me the answer. I hope things make sense to everybody here. Let me just very quickly dry run the answer. So I have these houses 27931. So I am defining my state max rob I as the maximum robbery that I can get from the ith till the end. So I want to compute the answer to max probability 2. So I have two options. So I will say the best answer for robbing the first till the fifth house would be two options, either to rob the first house. If I rob the first house, I will get 2 gold coins by robbing the first house. Plus, I will reduce my problem to a smaller problem of saying, let's now try robbing the third house, because second house can no longer be robbed. The second option that I had was that I can choose not to rob the first house, but I can now try robbing the second house. Does it make sense, everybody? This bigger problem gets reduced to two smaller problems. I can now solve this smaller problem M3 in the same way again. I can say either I can rob the third house or not rob it. If I rob the third house, I can say I will get 7 coins. Plus my problem reduces to robbing. This is 1, 2, 3, 4, and 5. If I rob the third house, my problem reduces. So I will get 9 coins. And my problem reduces to checking if I can rob the fifth house. So I will say plus M5. Or I can say that I will not rob the third house and my problem reduces to finding the best for M4. Similarly for M2, I will say either I can rob the second house, which will give me 7 gold coins. And if I rob the second house, I can now try robbing the fourth house. Or I can not rob the second house and try getting the answer to the third house. Now you guys would appreciate that I need not compute this M3 again, because this M3 would be computed here automatically, right? So I will just compute this once and not compute this M3. So what will I do? I will try computing M5. M5 says you can either rob it or not rob it. I would always want to rob it because there is no house going forward. So this is a base case which will give me 1 gold coin. So 9 plus 1 becomes 10. The second option that I had was 0 plus M4. M4 would again be divided into a smaller problem of either robbing it or not robbing it. I hope it makes sense to you, right? So you start from the first, start dividing into smaller problems, and then you keep on actually going till the base case and making sure that every subproblem is computed only once. Okay? What are the initial values? Initial value for everything would be, let's say, -1. That is, you have not computed it. The moment you compute it, you update the value there. Okay? What would be the base case in this case? The base case would be that when you reach M5, that is the only house that you are left to rob. You would always want to rob it. Okay, so M5 would be equal to 1. This would be a base case. I hope this makes sense to everybody. Right. So let's actually move to the next question. The last question is as follows. The problem is that there is a party going on. Okay, there is a party going on. And the party can be attended by N people. So there are N people who can go to the party. Every person in the party has two options. One option is that he or she can enjoy the party all alone by himself or herself. Okay, every person has two options. So let's say person I has two options, either to enjoy the party alone or to enjoy a party in a pair with any other person. Does the question make sense? There is a party going on. The party can be attended by N people. Every ith person in the party has two options. Option 1 is that you can enjoy the party all alone by yourself. Option 2 is that you can actually pair up with any other person in the party and enjoy the party as a pair. Now the question actually asks you that how many unique ways are there for those N people to enjoy the party? Does it make sense? Okay. So which company this question was asked at? This question was, I myself asked this question several times at Direct Eye, and I've seen this question being asked at several other companies as well. So you have to figure out how many different unique ways are there for those N people to enjoy the house party. Okay, cool. So let's actually take some examples. Let's say N was equal to 1. If there is only one person, how many ways that person can enjoy the party? There is only one way. The sad way is that he can only enjoy it all alone. So number of ways would be equal to 1. Does it make sense, people? Now let's say there are two people. Example 2, N equal to 2. There are two people in the party. Let's say number 1 and number 2. What are the ways that these two people can enjoy the party? One way would be that the person 1 is enjoying the party all alone. Okay. And person 2 is also enjoying the party all alone. This is one way. Second way would be that person 1 and 2 have paired up and they are enjoying the party together. Does that make sense? Are there two ways here? The answer to this problem would be 2. That number of ways would equal to 2. Okay, cool. Now let's actually take another example of, let's say, what happens if there are 3 people in the party. If n is equal to 3, how many ways do you see the 3 people enjoying the party? Okay, cool. So 1, 2, and 3, how many ways are there for the 3 people to enjoy the party? Let's actually formulate them. Either all 3 of them can enjoy the party alone. The second option is that the person 1 and 2 are enjoying the party together, and the person 3 is enjoying the party alone. Third option is that person 1 and 3 are enjoying the party in pair, and person 2 is enjoying the party alone. The fourth option that we have is maybe 2 and 3 are enjoying the party together, and 1 is enjoying alone. So there are 4 ways. This is 1, this is 2, this is 3, and this is 4. So number of ways in this question would be equal to 4. Cool. So we have discussed that for three people in the party, there are 4 ways to enjoy the party. Let's now actually try to see whether this problem can be solved using a dynamic programming approach or not. What were the features that we discussed? The first feature was optimal substructure. Do you see optimal substructure here? Let's try to figure that out. Let's say you already know the number of ways 3 people can enjoy a party, which we already know is 4. And let's say we already know the number of ways in which 2 people can enjoy the party, which we already know is equal to 2. Now let's say we know the number of ways 3 people can enjoy the party, we know the number of ways 2 people can enjoy the party. Can I actually figure out the number of ways 4 people can enjoy the party? Can I actually figure that out? To figure that out, do you try to answer the question that what is the element of choice for the 4th person? The 4th person, the first choice that he has is either to enjoy the party alone, or he or she can pair up with anybody else. Okay? Other option is that he or she can pair up. If he enjoys the party alone, do you think the problem reduces to the number of ways 3 people can enjoy the party? Let's say we already know the answer to the number of ways 3 people can enjoy the party, which was 4. Now the 4th person comes, and if he's enjoying the party alone, can you just say that just because he's not doing anything but enjoying the party alone, the number of ways would just be number of ways 3 people can enjoy it, and the 4th people joining them and not doing anything, so that's why multiplied by 1. Does that make sense, people? So you can say number of ways 3 people can enjoy the party multiplied by 1 if the 4th person is enjoying the party alone. On the other hand, if the 4th person decides to pair up with somebody, okay, you guys tell me which all people he can pair up with. There are 3 people in the party already. I am the 4th one coming. I decided I want to pair up with somebody. I have 3 options in front of me to pair up with them. Does that make sense, everybody? There are 3 people already in the party. I am the 4th one. I want to pair up. I can pair up with any one of those 3. So what will I do? I will say that I have n-1 options to pair up. So if I'm solving the problem for 4th person, there are 3 ways for me to pair up with somebody. Okay. The moment I pair up with somebody, let's say I paired up with the 2nd person. What does that mean? It means that the 2nd person and I are occupied. We cannot pair with anybody else, but the remaining 2 persons can do whatever they want to. So if you see that whenever the 4th person is coming and he has 3 options when he wants to pair up, if he pairs up with any one of them, now 2 persons out of these 4 people are paired up. So the remaining people that are left are n-2. And if you already know the answer of solving the best answer for n-2, you will just utilize that, which in this case is equal to number of ways for 2 people to enjoy the party. You will multiply that by the number of ways you can actually leave out 2 people, which is n-1. These are the 2 ways that you see. These ways are mutually exclusive and exhaustive. You can just add these 2 ways to get the answer to how many ways 4 people can enjoy the party. So what did I do? I have just proven that this problem shows optimal substructure, because that is the first feature that I need to prove to see if a problem can be solved using dynamic programming or not. How did I prove it? I assume that, let's say I know the answer for W2. That is what, say if there are 2 people in the party who are enjoying, how many ways they can enjoy. If I know the answer to it, let's say that is equal to 2. If I also know the answer to, let's say, 3 people enjoying the party, which is, let's say, 4, I already computed the answer to these 2 things manually. Now I am trying to utilize these two answers to compute the answer for 4 people in the party enjoying. So I am saying, can I actually get this answer using these two smaller answers? If I can do that, then I will prove that this problem has optimal substructure. So how do I prove that? I just said that for the fourth person, the element of choice is that he can either be alone in the party or can pair up with anybody else in the party. If that person chooses to remain alone in the party, that actually means that he is just joining the party, not changing any dynamics of the party. The number of ways would still be number of ways for 3 people to join the party. They can pair up, they can do whatever they want. I will just multiply a 1 with that because the fourth person is just going to the party and not pairing up with anybody else, not changing any other dimension, not changing any other part of the problem. The other option that the fourth person had was that he can pair up. If he chooses to pair up, he pairs up with one person. The number of people remaining in the party becomes n minus 2, which is in this case 2. I already know the answer to that problem, that how many ways 2 people can join the party. I will that multiply W2 with n minus 1, because for the fourth person, he had n minus 1 options to pair up with anybody. These are two mutually exclusive and exhaustive options. What is mutually exclusive and exhaustive? Mutually exclusive means that when you combine all these options together, you are not leaving. These two options do not have any common data point in them. So do we think that these two have any common thing in them? No, because one says that the fourth person is enjoying all alone. The other says the fourth person is pairing up. So there cannot be any duplicate answer in these two options. So these two options are definitely mutually exclusive. What do I mean by saying mutually exhaustive? Mutually exhaustive means that there is no data point which is outside these two options. Okay, because the fourth person can either choose to enjoy alone or he can pair up. There is no other option. So these two are mutually exhaustive as well. Whenever you see cases being mutually exclusive and exhaustive, you can just add them up to get the final answer. So we add them up, we get number of ways 4 people can enjoy the party is number of ways 3 people can enjoy it, multiplied by 1, plus number of ways 2 people can enjoy it, multiplied by n minus 1, and this is how we solve the answer. Okay, we can generalize it and say number of ways n people can join the party would be equal to number of ways n minus 1 people can join it. So that enjoy, the nth person is just going and staying alone, so you multiply it by 1. The other option is that the nth person decides to pair up with somebody. If the nth person decides to pair up with somebody, then the number of people in the party that are remaining to be decided is n minus 2, because 2 people have already paired up. N minus 2 ke figure out the number of ways, multiplied by n minus 1, because the nth person could have chosen to pair up with n minus 1 people. This is the recurrence relationship that I get. I have just proven that yes, this problem has optimal substructure. The moment I prove that this problem has optimal substructure, recursion can solve the problem for me. To move from recursion to dynamic programming, I need to look at the second feature, which is overlapping subproblems. Do I see the problems being overlapping? Do I see the problems overlapping? Yes, they are. Because when I will compute the answer for Wn minus 1, I will end up computing the answer of Wn minus 2 and Wn minus 3. And here also, if I'm computing Wn minus 2, and here also I'm computing Wn minus 2, why would I want to recompute it? I would just store all these n answers in an array or somehow maintain these states and utilize them to solve my answer. So yes, optimal substructure is also there, and overlapping subproblems are also there. So that's why you will now move from recursion to a DP solution, and you can solve this problem using DP. Let me do a dry run for this problem. Okay, so let me do a dry run. Before that, let me actually tell you what is memoization versus stabilization. Okay, so I would rephrase this question and ask that this question actually is about what is top-down versus bottom-up. I explained this briefly, but let me just explain that to you once again. Top-down simply means, do you guys appreciate till this point in time that dynamic programming solutions essentially can be represented as a recursive solution plus doing some memoization. What do we mean by that? DP, I told you, has two features. Every problem that can be modeled into DP has two features. One is that you have optimal substructure. The other is that you have overlapping subproblems. Okay. The moment you say you have optimal substructure, you should be pretty sure that you can solve that problem recursively. Okay, because there is optimal substructure, you can divide a bigger problem into a smaller problem and solve the problem recursively. The moment you see that there are overlapping subproblems, you can go a step ahead of recursion and say that just because the states are being repeated, I would just do memoization, which is nothing but having the values of the answers of those states saved and not computing them again. So that will DP in this way, nothing but a recursive solution, but throwing in memoization. This is something that we call as a top-down approach, that you just write the recursive code and just throw in memoization, because in the recursive tree, you will be seeing a lot of duplicate states. So this is one way of solving a DP problem. The other way is solving a bottom-up approach. Bottom-up approach basically is that you start with your base cases or base case, and utilizing whatever information you have, you compute the answer that you have for the next big state that you can compute. Okay, so using the base case, you compute a bigger answer. Now using all this data, you compute an even bigger answer. Using all this data, you compute even a bigger answer, and so on and so forth. So you are basically not solving anything recursively, but you are writing an iterative solution, that you are iterating from a base case answer and building solutions iteratively as you keep on going with bigger ends or with bigger problems. Okay, this, some people call this as tabulation. What does that mean by calling it tabulation? It means that you just have a table ready with you, which can be a 1D, 2D, 3D table. In every problem that we discussed today, it would be a 1D table, because we discussed 1D DP problems today. What does that mean? 1D DP means that the state, DP state, can be represented with one variable. That is what we mean by 1D DP. Okay, so tabulation means that you just create a table in which you say that these are the states that I want to compute. You fill the values for the base cases, utilizing them. So let's say you fill the values for the base cases, and utilizing them, you compute a bigger answer. Then you compute, utilizing all these things, a bigger answer, utilizing all these things, a bigger answer, and so on and so forth. So you just keep on filling your table, or in other words, you just do it the bottom-up approach. This is the second way of solving DP problems. So I hope this question should be clear now. Let's now come to dry running this problem. Okay, so let's now come to dry running this problem, and let me actually dry run this problem using the bottom-up approach, because top-down we have discussed very extensively. Let's actually discuss this using the bottom-up approach and try to dry run it. Okay, dry run the problem of party using the bottom-up approach. So everybody in the class knew that for n equal to 1, the number of ways for one person to enjoy the party is equal to 1, right? Now, number of ways for two people to enjoy the party is 2. We discussed that one, either both of them can enjoy the party together, or both of them can enjoy the party alone. We also discussed that we know the answer for what if there are 3 people in the party. How many ways can 3 people in the party enjoy? We knew that answer as well. We said that the answer was 4. So now let's say we only know the answer to way equal to 1 and way equal to 2. Now let's say I want to compute the answer for way equal to 3. I've already proven that this answer can be computed, has optimal substructure, has overlapping subproblems. So DP would be a way to go about it. So what would I do? Now let's say I know that one person is there in the party, and if only one person is there, there is one way. There are 2 people, there are 2 ways. Now the third person comes. The element of choice that this person has, so let me call it E or C. The element of choice that this person has is either to enjoy the party alone or to pair up. If he decides to enjoy the party alone, people, you tell me that the number of ways for 2 people to enjoy the party would still remain, because those 2 are still in the party. And this third person is just going on and tagging all alone. So you will say that the ways for 3 would, in this case, would be ways for 2 people to enjoy in whatever way they can, multiply by 1, because the third person is just tagging along. The other option that he had was to pair up. So what options does he has to pair up? He can either pair up with the person 1, or he can pair up with the person 2. Does it make sense, people? If he pairs up with person 1, how many people are remaining in the party to enjoy? I am the third person. I am paired up with the first person. So he's also busy. I am also busy. Only the second person is remaining. So that would mean that I would reduce my problem to finding number of ways one person can enjoy the party. Similarly, if I chose to enjoy the party, pair up with the second person, then I am busy, the second person is busy, only the first person is available. That would also mean that there is only one person in the party remaining, and there is only one way for him to enjoy. Well, ways one for him to enjoy. So you see that for pair up, you have ways one plus ways one. How many times are you adding ways one? That is the number of people who are remaining in the party. So in other words, you can just call this as number of ways one person can enjoy the party multiplied by 2, right? So what do you do? For 3, you get the answer by number of ways 2 will enjoy the party, which is 2 multiplied by 1, plus number of way 1 people can enjoy the party, which is 1 multiplied by 2, which makes it 2 plus 2, which is 4. So number of ways 3 people can enjoy the party is 4. So everybody please appreciate how we are tabulating. We started with the base cases, W1, W2. We now came to W3 using those two answers. Let me now compute the answer for base 4 as well. Okay. How can I compute the answer for base 4? Again, look at the element of choice. The element of choice that I have is the fourth person can either enjoy alone or the fourth person can pair up. If the fourth person enjoys alone, he will say that there are 3 people remaining in the party. Whatever ways they can enjoy, let them enjoy. I will just tag along and you will just multiply it by 1. The other option that he has was to pair up. He could have paired up either with the first person or with the second person or with the third person. If he pairs up with the first person is gone, fourth person is gone, 2 people are remaining in the party. They will enjoy the party in ways 2 ways. What if he pairs up with second person? Again, ways 2 ways, because 2 persons in the party are remaining. We can let them enjoy in ways 2 ways. 3, if you partners up with 3, again ways 2. So what is essentially happening? You are multiplying ways 2 with nothing but 3, because there are 3 people in the party apart from the fourth person. So you say for ways 4, my value would be ways 3 multiplied by 1 plus ways 2 multiplied by 3. Ways 3, I already know the answer was 4, so I will say 4 into 1. Plus ways 2, I already know the answer was 2, so 2 into 3. I say 4 into 1 is 4, 2 into 3 is 6. I say there are 10 ways for 4 people to enjoy the party. Okay, cool. So let's now actually come to the last question that I saw. So the second last problem that we had was that there are n houses. You want to figure out the best way you want to maximize your robbery so that every house has some gold coins. You want to maximize your robbery such that the moment you rob a house I, you can no longer rob the house I minus 1, and you can no longer rob the house I plus 1. So this was the constraint that we had. I said, again, let's look at the problem as a combination of, as some states. Okay. So let me define one state for you. Let me define a state which tells you that the maximum coins that you can get. So let me just move it and define a state for you. That is the maximum coins that you can get from looting the first to the nth house. So maximum coins that you can get from looting the first to the nth house. Let's say I want to compute this answer. Does that make sense? I want to compute that what is the max. Let's say I have a problem of finding the maximum coins that I can loot from the first till the nth house. Now I say that to look at this problem, you again have an element of choice. When you are at the first house, you can either to choose to loot the first house, that you can loot the first house, or you can not loot the first house. People, if you loot the first house, do you think you will get some gold coins? If you loot the first house, do you think you will get some gold coins? Yes, you will get some gold coins. How many coins will you get? You will get the coins that were there in the first house. Now, the moment you have chosen to loot the first house, your problem reduces. Your problem says, earlier the problem was to get the maximum loot from first to nth house. I have chosen to loot the first house. My problem reduces to a smaller problem. What does it reduce to? I have chosen to loot the first house. There is nothing left to loot in the first house. Just because I have looted the first house, I can no longer loot the second house. So my problem reduces to finding the best answer from looting coins 3 to n. Okay. So let me not call it coins I. Let me just call it a reward I. That if you choose to loot the ith house, this is the reward that you get. So reward 1. Reward 1 plus the sub-problem of coins 3 to n. Similarly, if you choose not to loot the first house, then what is the sub-problem reduced to? If you are not looting the first house, are you getting any loot amount? No, you are not getting any loot amount. So you will just add a 0 to a sub-problem. Your problem now reduces to finding the best loot that you can make from the second to the nth house, because the first house you have not looted, and if you did not loot the first house, you can actually still afford to lose the second house. So just by looking at this, you will realize that yes, there is optimal substructure, and I can represent my problem in a recurrence format by this. So if I want to figure out 1 to n, I can say it would be reward 1 plus coins 3 to n, or the best second option that I had was to not loot it and reduce into a problem of coins 2 to n. These are the two options that I had. I want to choose the option which will give me the maximum. So what will I do? I will explore both these options. Whatever comes out to be the maximum of the two, I will return that as the answer. Okay. So now this is the recurrence. This is from 1 to n. Let me just generalize it. So it becomes coins I to j. If I have the house from I to j, I want to loot them. Or let me actually call it I to n, because n is going to remain there forever, the way we have described this problem. Coins 1 to n would equal to, one option is that you actually loot the ith house, you get the ith reward, plus you reduce the problem into I plus 2 से लेकर n तक, or you choose not to loot the house plus coins I plus 1 से लेकर n तक. You take the maximum of the two. Now this is the recurrence relationship. The moment you arrive at this recurrence relationship, you know that this problem can be solved using recursion. Okay, you know that this problem can be solved using recursion. Now, before that, let's make sure that we also know the base cases. So what are the base cases? You see that this definition fails to hold true when you are at the last house. Because if you are at the last house, do you think that you can actually go to the n plus 2th house? No, because that house does not exist. So if you are at the last house, that should be a base case, because this recurrence relationship will not be able to define it. So what should be the base case? One base case would be coins n to n. What does that mean? That is a sub problem which says that there is only one house to be looted, nothing else is there. What would be the best answer that you can get? My submission would be, if there is only one house, what should you do? You should drop that house, right? Because there is nothing better that you can do. So coins n to n would equal to be the reward of looting the nth house. So this is one base case that you can see. Now you guys tell me, if I am at the n minus 1th house, will this recursion help me then also? It will not, because if I am at the n minus 1th house, I will be forced to go to n minus 1 plus 2, which will be n plus 1th house. That house does not exist. So even for n minus 1, I should have a base case. So the second base case that I would have would be that what is the best answer for for looting the houses from n minus 1 to nth house. Now my summation is that if you have only two houses, n minus 1 and nth, can you loot both of them? No, you cannot loot both of them. Should you loot none of them? No, you should not loot none of them. At least you should not loot one of them. In fact, you should exactly loot one of them. If you should exactly loot one of them, which one of them will you loot? My summation is that simply loot the house which has the maximum reward out of them. So if the n minus 1th house has the maximum reward, loot that house. If the nth house has the maximum reward, loot that house. So yeah, now you know that you have a second base case as well. Do you require a third base case? So does this problem hold true for n minus 2? Yes, this recursion hold true from n minus 2th house, because from n minus 2 you will be forced to go to n minus 2 plus 2, which is n, and that is still a definition which is defined in this recursion. So that's not an issue. So these two base cases should be sufficient. So till this point in time, we have discussed that yes, recursion can solve our problem. Now you see that a lot of states would be repeated here. If you just solve this using recursion, a lot of states would be repeated. I am leaving that as an exercise for you guys to figure out that how these states will be repeated. I will give you a hint How to figure that out? Just build a recursive tree and see that a lot of states are being computed again and again. So what do? You memorize those states. Okay, you memorize those states. That's it. The moment you memorize those states, you just solve this recursive question, add that memoization, you get the answer. You get that answer top down. If you want to solve that answer bottom up, what do you do instead? You start with the base cases. So you start with, what if I only had the last house? The answer will be reward n. What if I had the second last house and the last house? The answer will be maximum of two of them. Now if I have the answer to these two cases, can I actually figure out the answer from n minus 2 to n? So what I'm saying is, let's say I know the answer. If I only had this house to loot, then what would be the best answer? So let me just actually take an example, real life example. So let me take an example and see what would be the answer there. 2, 7, 9, 3, and 1. So let's say I know the answer. This is my base case, right? The last one is my base case. The answer would be that you can get only 1 coin, right? So the answer to 5 would be 1. The second last is also a base case. The answer to 4, as we discussed, would be maximum, that you can either choose to loot this one or this one. Maximum of 3, 1, which happens to be 3. Now you come to this point. If you are actually doing it bottom up, so you have the base cases. Using the base case, you solve a bigger problem that you can just solve using the base cases. So if I have these 3 houses, what is the best thing that I can do? I have 2 options. Either I can choose to loot this or not to loot this. If I choose to loot this, the second option is choose not to loot this. If I choose to loot this, I will get 9 coins because I'm looting it. And just because I'm looting it, I cannot loot the 4th house. So I will be forced to only consider the answer for the 5th one, which I already know this one. So this will be 10. One option gives me answer 10. Second option is I do not loot this house. So I will get 0 coins from this one. But I can still manage to loot the 4th one, which gives me 3 coins. So the answer would be 3. So I take the maximum of 10 and 3. So the maximum is 10. So I know that for this, for answer 3, the maximum answer that I can get is 10. Now using these 3, I can compute for this. Either I can loot it, not loot it. If I loot it, it would be 7 plus answer of 4. If I not loot it, it would be 0 plus answer of 3. Answer of 4 is nothing but 3. 7 plus 3 is nothing but 10. Or you can say 0 plus answer 3, which is nothing but 0 plus 10, which is 10. You take the maximum of 2, which is 10. So you say even for this, answer of 2 is also 10. Now you are left with this one. You again have 2 choices, either to loot it, not loot it. If you loot it, you make it 2 plus. If you loot it, you get 2 coins just because you are looting it. It becomes 2 plus answer 3. Or it becomes 0 plus answer 2. 2 plus answer 3 is 10. Answer 3 is 10, right? Sorry, answer is 10. 2 plus answer 3 is 12. So one option is 12. Or if 0 plus answer 2, which is 10. The maximum of 10 and 12 is 12. So you say that if for the first house the answer is 12, so now you know the answer that if you want to loot from the first till the nth house, the best thing that you can do is get 12 coins. Okay. So today, what did we discuss? We discussed what is dynamic programming. We now understand that any problem which shows optimal substructure and overlapping subproblems is a problem which can be modeled into a DP solution. We know that the moment a problem shows optimal substructure, it can automatically be solved using recursion because you can divide a bigger problem into smaller problems. Now, the moment apart from showing optimal substructure, it also shows overlapping subproblems. You can essentially store the subproblems answers and utilize them the next time you see them. So now you actually move from recursion and go to a dynamic programming solution. Okay, so DP in one way is nothing but recursion plus dynamic programming, recursion plus memoization, because you see some problems being repeated. Okay, this is one way to look at it. The other, this is the top-down approach. Bottom-up approach would be that if you have proven that you have optimal substructure and overlapping subproblems, start with the base cases, utilize those base cases, and get the answer to the next case that you can get, and then utilizing all this information, get the answer to the next thing that you can get, and so on and so forth. You keep on building your answers, you will get the entire answer. Okay, this is the bottom-up approach that we have. Apart from that, let me explain you some more things. Then we also discussed that how to figure out whether a problem can be solved greedily or not. The problem can be solved greedily If by just looking at something without looking at what holds for you in the future, if you can make a greedy choice, which will always give you the best possible answer. If you can make such a choice, a greedy solution will work. Okay, if you cannot make such a choice, you are bound to explore all possibilities. Then you should think the DP way. How to think the DP way? Look at the element of choice. Look at any element. Look at what element of choice do you have. Either you can include it, not include it, do something with it, not do something with it, and so on and so forth. The moment you look at the element of choice, you can, looking at the element of choice, construct a recursive definition of the problem. You can construct a recursive solution. You can just create a recurrence relationship for that problem. The moment you do that, then you need to figure out, do you see overlapping subproblems in that recurrence? If you see overlapping subproblems, just memoize it, you get a DP solution. So this is just in brief what we discussed today. We discussed several questions today. This was the basic building block class of DP. Stay tuned to Scalar Academy and keep a tab on all the videos that we keep on sharing with you guys. All the very best for everything that you do. Goodbye. Good night.